Okay, this should be short, or at least shorter. Um, we're just going to cover a few things as far as the magnetic field and magnetic forces. Last time we just finished up talking about what magnets are, how they work, talking about their poles, and then the magnetic fields that run from the North Pole to the South Pole. Um, we also talked about how if a charge is moving, that's going to generate a magnetic field. And since a moving charge produces a magnetic field, it follows logically that a current, which is just moving charges, also produces a magnetic field. So not only just single particles, but multiple in a current flow. So you can imagine over here on the right, if we have a wire that has an electric current running through it, we'll have maybe the current's flowing upward. So we'll have lots of electrons in here, and those are charges in motion. When this happens, the magnetic field surrounding a current carrying wire can actually be detected if we just put a bunch of compasses around it, just like here in the picture. Um, they, as we know, will align themselves to the magnetic field, which means magnetic field is actually going to be in a ring around this current carrying wire. If we move these compasses out a little bit, maybe instead of 2 inches away from the wire, we move them out to 4 inches away from the wire, what we would find is they remain in this ring all pointed in a circle. So what we're actually seeing is that with a current carrying wire, the magnetic field lines are concentric circles, which means if we were to even go inside, we would have a smaller one on the inside. Of course, whenever the current reverses direction, the compass needles will actually turn around and then point in the opposite direction. So that means if the current reverses direction, the magnetic field will also reverse its direction. So you'll notice in the first picture, we don't have any arrows drawn on this, but that's okay. Since the current is pointing up, we know that the field line should be pointing this direction. Same thing down here, since we know the magnetic field is looping around from the front to the back, we know that the current is moving in this direction. Now, what's really interesting is if you take a wire, like down here in the bottom right-hand corner, and you fold it into a loop, you get inside the loop, you get this place where all the magnetic field lines are pointing in the same direction or in the opposite, or yeah, they're all pointing in the same direction. So they all come out of the loop or they can all go into the loop depending on which way your current is. Um, this is essentially just because the magnetic field lines are just bunched up inside the loop. So again, we can see with the iron filings, we have these filings following the magnetic field lines. Then we have a single loop here. You can see these get bunched up sort of in here. And they're all pointing the same way. So we don't know what way the current's flowing in this right now, but we'll just assume these are all going through from right to left. And then if you actually add more loops, you create what's essentially called a solenoid. And what's really nice about solenoid is that the field inside is literally just the sum of the fields due to each current loop. And you can see that the magnetic field inside a solenoid is very well formed. So you get this nice linear magnetic field inside these solenoids. So if you ever wanted to, like, shoot a iron ball bearing or something across the room, you could use a solenoid and put it in one side and actually turn on a current through your solenoid, um, like this. So if this is our solenoid, you can actually launch a metal like ferromagnetic ball that way. Now, there's other things we can do if we drop a piece of iron inside of a solenoid. Um, if we put a piece of iron in there and turn on a current in that wire, then the without a piece of iron, let's back up. Without a piece of iron, just turning on a current carrying coil with a current, that actually creates an electromagnet. Essentially, that's just a magnet that is only a magnet when there's a current in the wire. So only a magnet when there is a current. Okay. The strength of this thing will actually increase by either increasing the current through the coil or increasing the number of turns in the coil. And we saw that on the previous slide. You get a nice, better, well-defined field inside the solenoid if you have more turns in it. Now, if we even put like an iron nail inside this coil, you can even get more strength. You can see that here in this bottom picture. There's a nail through this current carrying core, and then all of a sudden you have an electromagnet. Um, and essentially what this does is it utilizes the domains inside the iron nail. Uses domains inside. And we talked about that last time. Of course, and we've talked about superconductors before, but for even stronger magnets, you can use superconducting magnets. Some of the most powerful ones that I can think of are the superconducting coils that don't use iron cores out, but they are able to handle large electric current flows, and they have no heat loss. And these magnets are in the Large Hadron Collider at CERN in Geneva, Switzerland. So this is the world's largest particle accelerator. Basically, in this giant ring, it's underground, so this is just a picture of where it is, but you can actually see it from like an airplane. What it is basically a very large particle accelerator where they accelerate particles, some going one way, some going the other, and then they measure what happens when these two beams of particles actually crash into each other at various places around the ring of the particle accelerator. So how this is done is essentially you've got this relatively small path for particles to go through. That's essentially the pipe that they're in. But then you have all of these like magnetic coils around the sides. And I believe these are cooled down to be like just very, very cold, like just almost 0 Kelvin, I think. And that causes them to be essentially superconducting with no heat loss. And that those magnetic fields are what drive those charged particles around the ring. We could talk about exactly how that works now. So we know that a magnetic field will influence a moving particle. So a charged particle at rest will actually not do anything with a static magnetic field. So if your particle is not moving and you have a magnetic field, it will not interact. But if a charged particle is moving in a magnetic field, you got to have that movement. When you get that movement, that's when you actually get to interact with the magnetic character of the charge. Okay. When this happens, your charged particle actually experiences a deflecting force. And the magnetic force is greatest when the particle moves in a direction perpendicular to the magnetic field line. So let's slow down and think about all of these points here with just this picture. So we certainly have electrons coming in because it is an electron beam. So that is certainly a moving charge. Okay. And it's going to fly in between these two poles of a magnet. So it's definitely it's going to be a moving charge that's interacting with the magnet. Interaction. Okay. Now let's think about which way the magnetic field is going to point. So remember, the magnetic field is going to go from the north pole to the south pole. Okay. So now we have a velocity vector. Remember, velocities of magnitude and a direction. So these electrons have a velocity. Ooh, that's not a straight line for a vector at all. Give me one moment. I want to fix that because it's hideous. And now, of course, I can erase. There we go. Okay, so we have this velocity vector. Let's even use a different color. There we go. So here's our velocity vector. Our magnetic field could be represented as a vector 2. So maybe we include these vectors this way. We have them over here. We also have the beam, which is just the velocity. I'm going to use the letter B. That's typical what you use for the strength of a magnetic field. So B with the little vector hat on top. Now, what's interesting, I'm going to make this really cluttered. I apologize. But you would think that the particle would just keep going straight, but there is a deflection force. It's deflected up by some angle. So it turns out you have to have vectors pointing in 3 different directions. You have to have the velocity or the beam in one direction. So here you see the velocity of the beam in one direction. You have to have the magnetic field in another direction. And then the force acting on this is actually going to be in the third direction. And this is always the case for charged particles moving in a magnetic field. Notice how we have a perfect 90-degree angle here. When this angle between the magnetic field and the velocity of the particle is 90 degrees, that's your maximum force. So let's recap all of those things because that was a lot to take in. So we know that the magnetic force is greatest when the particle moves in a direction perpendicular to the magnetic field lines. We just showed that. Well, if the magnetic force is, if the particle moves parallel to the field, so if the particle is moving, here's our velocity, if the particle is moving this way, and it turns out the magnetic field also points this way, well, then the magnetic force is 0. F magnetic equals 0 newtons. There we go. So you can see we have a maximum when it's perpendicular. Let me do it this way. A maximum when it's perpendicular. We have a minimum value when it's parallel. So that means the paths in between, maybe it's at a 30-degree angle, maybe it's at a 20-degree angle. Those are actually going to depend on the sign of the angle. So we can actually write out an equation to calculate this force. So the force that deflects an electron beam, if it acts perpendicularly or it really acts in any direction, it's got to be the force that you're going to get out of this is always perpendicular to two things. It's perpendicular to the magnetic field and the electron beam. You can see here we have a 90-degree angle between the force and the beam, and a 90-degree angle between the magnetic field and the force. So you can break this down and make it essentially Q being the charge of the particle. So we know this is essentially going to be an electron. So it's going to be a negative value. V is the velocity of the particle. B is the strength of the magnetic field. And then sine of theta, we got to be careful here because this is the sign between the sign between these two vectors. You might be tempted to think that it's this angle, but it is not that angle. It is the sign between the two vectors from the velocity and the magnetic field. So I'm going to put a big red X over that. That is not the angle. The angle is between these two things, V and B. Now, if a charged particle moves through a magnetic field and experiences a deflecting force, then obviously a current or charged particles, multiple, plural, moving through a magnetic field will also experience a deflecting force. So if we have a wire that's carrying a current through a magnet, it's either going to be pushed or pulled by the magnetic forces, depending on which way the magnetic field is turned. So the force is perpendicular to both the field lines and current, and you can essentially think about the force of the magnetic field as a sideways force, since it always points out to the side. We showed that with the two vectors, and then the other one coming out in a third dimension. So you can see we've got a current going this way. So we have the velocity of these electrons. We have the magnetic field in here, and then our force is going to be going up. And if we reverse that current, you'll notice that the current's changed. Then that changes the sign on the force, and the force is going to point down. And what's really cool is we can use this idea of a wire moving or using this like electromagnetic force conversion into mechanical. We can actually make a sensitive current measuring instrument called a galvanometer. Usually it's a lot of loops of wire inside of a galvanometer. And you can see that down here. So you've got this coil, I've labeled it here, and you can see we've got lots of wires coiled around this drum. And essentially what would happen here is you can calibrate these, right? Because this needle, let me label it in red here, this needle here is going to move, right? That coil of wire wants to move because it's going to have forces on it when a current goes through it. So whatever current goes in, so I in, whatever current goes in, we can calibrate the galvanometer to, as the current goes through, it will also correspond to just the current itself, or we can calibrate it to tell us what voltage would be there to cause that current. When we do that, if we calibrate this galvanometer to measure the current, it's just called an ammeter. If we calibrate this galvanometer to show us the voltage instead, it's going to be a voltmeter. And you'll notice that both of these pieces of equipment here, they look the same, and they actually both just have run-of-the-mill galvanometers in them. But you'll see they've been calibrated to read two different things. You got one reading current, amperage, and the other one reading volts or voltage in volts. We have amps here and volts here. And the whole idea is that there's just those coils inside of wire. So when a current goes through, it's just going to cause those to rotate. we can take this idea of a galvanometer and actually see this in electric motors. So in a motor, the current is made to change direction every time the coil makes a half rotation. So normally what would happen is your coil would just rotate halfway and stop. So it would start, if this was your coil of wire, it would start one way and then sort of just rotate until it aligns, and then it's going to stop. That's typically what would happen. But after that half rotation, if you change the current and reverse it and time it just right, it'll actually complete a full loop. So the whole idea here is to get a full 360-degree rotation, you got to have that AC current flipping back and forth. That's what's going to drive your motor. So that's a crucial key here to actually how these motors work, because they'll be AC motors, alternating current. So that's all I needed to say about the electric forces and electromagnets. This should be enough information for you to get through any problem sets or labs. The next lecture is just going to be applications and examples of where you can see these electric forces and electromagnetism out and about in the real world.